That's okay. Go ahead. What we said yesterday, Kaylin, was the bigger the star's mass, the shorter their lifespan. The bigger the star's mass, the shorter their lifespan. More mass, shorter. Smaller mass, lives longer. And we also said that the Earth has a solar mass of around 1. Go ahead. Sharpened? Good. Next time, sharpen before the lesson if you can. Just hang on, Raph. Okay? The sun has a solar mass of about 1. It's going to live around 10 billion years-ish, plus or minus a few. We're going to start looking at 3 main types of stars. We looked a little bit at intermediate stars, intermediate mass stars. The sun is an intermediate mass star. It's a yellow star. It's pretty hot. And we had just got to low mass stars. So pick up right here, please. This is the top row of your star pathways sheet. So if you look at your star pathways, oh, I don't think I printed that yet, Mr. Dewick. That's this color sheet right here. This picture. Yeah, it'll take a bit of time. So the top row, this is the low mass stars. So if you're looking for kind of a context, you can look at that as we're writing this down. Low mass stars start small and stay small. They're only about 10% of the size of the sun. We use as our reference frame the sun because it's the closest star to us and it's the one we're most familiar with. Low mass stars are called red dwarfs. About 10% of the sun. Do I have that in brackets next to there or not? You can just put right next to there 10% of sun. They burn very slowly.
10%.
Yep.
Because on his screen, it looks slightly different.
Yep, I know. I had to make the font larger, and also, if I just did the notes, I can't include all the pictures and things, and I want to show you some cool pictures. Low mass stars burn very slowly. They may live 100 billion years. And the reason I said they may live is our universe is only about, I don't know, 13.8 billion years old. So we think they'll live 100 billion years, but we have no experimental proof because the universe isn't old enough for us to have seen one of these stars die. The math suggests they'll live about that long. We've seen some stars die, but the low mass ones live so long we haven't seen those stars die.
What's the answer for the eventually become?
I'm getting there. Patience. Okay? You can tell me what they become by looking at that star chart, that colored chart on the top row. What do the red dwarfs eventually turn into? White dwarfs. They eventually become a white dwarf. So do you need to memorize this? No, that's why I gave you a color chart. Do you need to be able to kind of understand what that chart is trying to tell you? Yeah. So those are the low mass stars. That's the top row. Okay? Yep. What is yours? Okay, let me check the notes. I retyped these and I might not have fixed. After low mass stars, we have intermediate mass stars. That's the middle row. These burn hydrogen faster. They last, and I'll put in air quotes only because it's still a long time, around 10 billion years. Our sun is a low mass star. So here's what's probably going to happen in our future. Close to the end of their life, they expand, can you put your phone on vibrate, please, into a red giant. Can you see that on the middle row on that little star map chart? They shed most of their material, and then they collapse. becoming a white dwarf, and then eventually becoming what we call a black dwarf. I'll bring those notes up again in just a second, so hold on. So here's what we're getting at. You can see it in the chart. Most of an intermediate mass star's lifespan, it's doing its sun thing like our sun is. It's just shining. But near the end of their life, they expand into a red giant, and then they collapse into a white dwarf, and then eventually they become a black dwarf. The bottom row are the high mass stars. These ones are pretty cool. Oh, the sun will become a red giant in about in about 5.5 billion years. Give or take a billion years either way, Nick, but who's counting? I don't plan on being there. Okay? And I think I told you last day, when we calculate how big the sun will be as a red giant, because there's some uncertainty, the Earth will either be just inside the sun at that point or just outside the sun. But either way, we're toast.
It's not intended.
No.
Because there's red.
The bottom row are the high mass stars. These are huge, and they consume energy way faster. You can just write faster, but way, way, way faster. Yep. Yep. I'll build a break in about half an hour. Okay. So the high mass stars live for only about 7 billion years. These ones, Jaden, we have seen die because our universe is about 13.8 billion years old. So as we've observed out in the universe, we have seen some of these. But there is a huge range. Some might only live a few million years to 100 million years to 7 or so billion years. They become supergiants. Way faster and range are the gaps, and then they become supergiants, and they collapse. They collapse in on themselves, and they cause dramatic explosions called, who remembers, we looked at this term yesterday, this is a supernova. Plural of supernova is supernovae. When a star goes supernova, for that split second, it gives off more light than the entire galaxy. Let me say that again. When a star goes supernova, for that split second, it gives off more light than all the rest of the stars in the galaxy combined. They're huge cosmic events. They can be so bright that they can be seen during the day from the Earth, but none has been that bright for 400 years. However, put your pencils down and watch the screen. We do have a ticking time. I got to tell you about this part here. This is not in your notes, but Betelgeuse is a star nearby. It's a ticking time bomb. It's expected to go supernova very soon. And by very soon, we mean next week or to a million years from now, which on the cosmic scale is, if it goes supernova, it will probably be visible during the day, and it would be brighter than the full moon at night. It wouldn't affect us at all, but it would give us a spectacular view. I'm hoping, this sounds weird, but I'm hoping it goes supernova during my lifetime because I want to see it. Cassandra, hustle back, kiddo. Mask up, hustle back.
Does anyone know what a supernova will look like?
Yes. Can you remind me on one of our blended sessions, because it's very obscure, I'll show you something that Einstein proved called gravitational lensing, which actually allows you to see the same event in space more than once because the light has been curved and has arriving from different areas at different times. And so we actually used that to predict. We saw a supernova after it had blown up, and we said, wait a minute, the light from that explosion should be arriving from over here in about 4 years. We pointed the Hubble there, and sure enough, we saw it. We had to do some pretty complicated math. It's pretty cool. Keep going. If the star is about 10 to 15 times the size of the sun, it will collapse into what we call A neutron star. Can anybody guess what the main particles inside of a neutron star might be?
A neutron.
Neutrons, okay? It's so dense that all of the protons and electrons are so smooshed together that they fuse and become neutrons. So you can't, a lot of our normal chemistry rules don't apply here. A star that was maybe 1 million kilometers wide will now be about 10 kilometers wide. A star that is 1 million kilometers wide would be about the size of Pitt Meadows. Put your pencils down. Neutron stars are cool. So those are neutron stars, but then we get to something even cooler. So if a star is 10 to 12 times the size of the sun, goes supernova, it will typically collapse into a neutron star afterwards. If the mass of that star was 25 times that of the sun, it will become a
Supernova.
Black hole.
black hole. In a black hole, the gravity is so strong that nothing, not even light, can escape. We can detect black holes because we can see light from distant stars actually being curved and distorted, and there's nothing there to do the distorting. There's a black hole there. 5 minutes.
Where's a black hole?
Pardon me?
What's a black hole? What does it do?
So what does it do? Good question. Hustle back. Black holes don't swallow everything up like a giant vacuum cleaner. Did I not paste this in your notes?
Nope.
Okay. But you can look up and pay attention anyways. If you were some distance away from a black hole, the black hole's gravity would behave like a regular star's gravity. But you wouldn't be able to see anything. Let's try that again, Mr. Dewick. You wouldn't be able to see what, you know what, no word there. You wouldn't be able to see what was causing it. So gravity is what holds you to the Earth. To leave the Earth, we need to achieve something called escape velocity. Escape velocity is about 11 kilometers a second. If you have more gravity, you need a bigger escape velocity to escape. The sun has a larger escape velocity because it's got stronger gravity. So what's a black hole? A black hole has such a strong gravity that even light can't escape. And so to go faster, to escape from it, you'd have to go faster than light, and nothing can go faster than light. So the answer to your question is a black hole is an area of space where escape velocity is bigger than light speed, which means you can't escape from that area. I don't think I included this in your notes, but once you get very close to a black hole, you pass the event horizon. That's the no coming back place. Once you cross the event horizon, nothing in the universe is getting out.
What's an event horizon?
That's the area right then where the escape velocity to leave from that area would be bigger than light speed. If you're further away from the event horizon, you still got a chance at getting out because you can travel at a speed, there is an escape velocity that you can travel at, but as soon as you cross the event horizon, to get out of that area, you'd have to travel faster than light, and nothing can travel faster than light.
Except for me.
Once past this black hole's gravity is so strong that you would need to travel faster than light to break free. Since nothing can travel faster than light, nothing can break free.
Where is this?
I didn't include it in your notes. This is nerd trivia.
What was the
So what would it be like if you fell into a black hole? We're going to use our imaginations. Look up. Let's suppose, hang on a sec, Pat. Let's suppose you were falling feet first into a black hole. As you got close to the event horizon, there would be a different gravitational pull on your feet as compared to on your head. You would actually feel as though the top of your head and the top of your feet were getting pulled apart a little bit. And at first, it would feel pretty good. Like when you stretch in the morning, it would feel all right. But very quickly, it would go from feeling pretty good to owie, 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 owie. And in fact, the difference in the tug on your feet versus your head would eventually become so great that you would bifurcate. You would split in half right around the middle. And then each of those two pieces would eventually split in half, becoming 4 pieces, becoming 8 pieces. becoming 16 pieces, becoming 32 pieces, becoming 64 pieces. Not only that, the black hole's gravity is so strong, it actually warps the fabric of space-time. You would actually be getting compressed together from all sides, sort of like toothpaste being squeezed through a toothpaste tube. And eventually you would end up as this single row of atoms streaming down, infinitely down, never to return to the universe.
Where were the atoms?
And we have a name for that. What's the name for that, Tabby?
Spaghettification.
That's
Spaghettification.
So, what was if the mass was 25 times the sun, it would become a black hole?
Black hole. So this is what we call spaghettification. It's a nice word to have in your vocabulary. Put your pencils down. Watch the screen. I got about 10 more minutes, but I want you to zone in because this is what the homework's going to be. So Cass, put your phone away, please. Yep, can you put your phone away now? Can you turn that star chart over to the back page and you'll see something called a Hertzsprung-Russell diagram. Yep, the back page. Other page. Yep. So, how do we classify stars? They're far away. How the heck do we know whether it's a small or an intermediate mass or a high mass star? We use something called a Hertzsprung-Russell diagram. I've given you one in color because they really need to be in color. Hertzsprung and Russell were two astronomers who cataloged hundreds and hundreds and hundreds of stars looking for patterns. This is a diagram that compares the brightness and temperature of various stars. By comparing the brightness, luminosity, fancy word, and temperature, color, of various stars, we can put them on a graph and we can figure out what category stars belong to. So in your notes, I gave you a chart. We're going to classify some stars. So I've given you a Hertzsprung-Russell diagram. That's the color picture. But I also, I think, gave you a graph in your notes. Yes? So the first star, mystery star number 1, has a temperature of 28,000 degrees and a luminosity of 0.00. Okay, folks, I need you with me here. This is what the homework's going to be. Has the temperature of 28,000 degrees and a luminosity of 0.0001. So if I was trying to find that, 28,000, about there-ish, give or take. I've scrolled down. What was the luminosity? So the temperature is on the x-axis. Okay? So where would 28,000 be? Well, that's 25,000. That's 45,000. It's going to be a little bit to the left of 25,000. Okay?
I found it.
Hang on. What was the luminosity? 0.0 what? 2 zeros and a 1? 3 zeros and a 1? So it's going to be right about there. And now what you need to do is you look at the Hertzsprung-Russell diagram, this chart right here, and you, upside down. So if I hold this by this graph, I'm down here. What kind of star would we classify that as?
White dwarf.
Probably a white dwarf. Okay?
Yes,
Yep. And what color is it? White. Okay, sorry? Question? Let's do another one. So the next mystery star, it has a temperature of 4,000 and it's 0.001. So again, 4,000 is probably halfway between 3,000 and 5,000-ish. What was the temperature, Nick? I've scrolled down. How many zeros? The second one we're doing? 2 zeros. So here, right about there-ish. You okay with that? So we look at our Hertzsprung-Russell diagram. Right around there. Probably a red dwarf. Okay. Yep, that's okay. And what color would the red dwarf be, Captain Obvious? Red.
Yes.
Mystery star number 3 has a temperature of 2,000 degrees. That's going to be probably right about there-ish. And what was the luminosity? I've scrolled down. Jada, what was the luminosity? 10,000? So 10,000 somewhere up here. Look at your Hertzsprung Russell picture. Probably a red giant. And again, what color, Captain Obvious? Red. See how we kind of read this, Nick? Is that okay? Do 2 more, and then I'm going to give you some stars to classify. Sorry? Okay, I'll walk you through it. So mystery star number 4, what's the first number, Cassandra? 9 what?
9.
So that's going to be the temperature, which is the bottom scale. Where would 9,000 be? Now, it's a weird scale because it goes from hottest to coldest, but I think 9,000 would be kind of right about there-ish. And what was the second number, the luminosity? I've scrolled down. Could you tell me? 66,000? Wow, that's bright. So 66,000. Cassandra, what number is this second number from the top? 10,000? Here's 100,000. About there. So now look at your color picture. What prediction would you make? Supergiant, I think. Yes?
Yeah.
This is how we classify them. And we've classified thousands and thousands of stars this way, so our data is pretty good. We confirmed it. Sorry? So if you hold your diagram up like this, see we're right there on the graph, we'd be right about here in the diagram.
Oh, I see.
Yep. I couldn't figure out a way to do color and a graph paper. I tried. So the graph paper is going to be on a separate piece of paper, but actually that's easier because that means you can draw on it, which helps, I think. I don't know. What color is it? Yellow?
Oh, we're actually following up.
That's why I printed it up in color.
I think it's like orange from where it would be on the back.
Okay, I would take that too. I wouldn't take blue, and I wouldn't take white, and I probably wouldn't take red. Phone away, Ariel. So you could say yellow or orange. Last one. Mystery star number 5. So it's got a temperature of 27,000, which would be, I don't know, right about there. And it's got a luminosity. It's got a luminosity, hey Sadie, of about 650. Kind of about there. Okay.
Just a sec.
Yep. So, what kind of star would that be, where the red dot is, if you had to make a guess? Again, we look at our map.
Red dwarf?
I don't know.
Maybe like
Red giant?
white star, maybe.
Looks like, you know what? It looks like it's a main sequence and a massive star. And what color? You're right. What color did you say? White. So I would call it a main sequence star or a massive star because that particular one doesn't seem to have a special name, but I can definitely tell you it would be white. Main sequence. I would take blue-ish because here's what I would, it's really, what wouldn't I take? I wouldn't take red. I wouldn't take orange. Whitey blue, sure. Is that okay? So that's how we use a Hertzsprung Russell diagram. Most of the stars, yeah, we're continuing from last day, sorry kiddo. About 90% of our stars are along this middle band. So your homework, I'm going to give you now, I'm going to give you some stars to classify. The classifying stars, I didn't give you an answer sheet for. We'll go over the answers either later in class or on next class. The homework, I did attach the answers for.